course, here I need to start recording again. And the idea here is that we are facing the situation, let's say, that we have, let's say, someone called a dealer. And this dealer wants to have a particular secret information, S. And this secret information, S, he wants to, let's say, share it with a certain number of parties. So let's say that we have 3 participants like P1, P2, and P3. So he wants to give them the secret, but not the entire secret to each of them. Because the idea is that, let's say that the dealer is not trusting any single participant, but he's saying, okay, I can trust at least a combination of a subset of participants. So the idea is that he's going to share this secret in different shares, B1, B2, and B3. And then he will distribute these shares to the participants. So the sharing is done in such a way that, for example, any 2 out of 3 participants can reconstruct the secret. So we have this particular combination here can get the secret by combining B1 and B2. This particular combination here can reconstruct the secret by combining B2 and B3. And finally, this combination can reconstruct the secret. So this is what is called in general 2 out of 3 secret sharing scheme. Okay. Why 2 out of 3? Because we are having 3 possible players, and the threshold in order that is required to reconstruct the secret is 2 players. So any combination, any subset of 2 players out of 3 can reconstruct the secret. On the other hand, we have, let's say, a very strong guarantee that any single player cannot reconstruct the secret, in the sense that it cannot or she cannot gain any information on what is the value of the secret by just having at his disposal or her disposal the corresponding share. So this is in particular called threshold secret sharing. And how do we construct these secret sharing schemes? So in general, we could have something more generic than this. So we can have, let's say, 2 out of n threshold secret sharing schemes, which means that we are always keeping threshold 2 players to reconstruct in a unique way the secret, and n players, so larger than 3 also. Or more in general, k out of n threshold secret sharing scheme, where k is smaller than or equal to n. If we have k is equal to n, then it means that all players are necessary in order to reconstruct the secret. So originally, this was thought as a technique to safeguard cryptographic keys. The idea is that the dealer might be someone, like let's say, some kind of government institution that wants to give access to other, I don't know, subsidiary agencies or institutions, like, I don't know, FBI and NSA or whatever you choose, access to some sensitive information, for example, information that have been encrypted under a particular secret key, but this dealer does not want to give the entire key to each single enforcing agency. So it doesn't want to run into the situation that, for example, FBI can access these data by itself without asking for permission And the dealer, on the other hand, is saying, okay, if both like two parties are colluding, like FBI and NSA or CIA are colluding, then they can reconstruct that. So I trust that their collusion is safe in a certain sense. And the idea is to safeguard these cryptographic keys using this particular type of schemes. But now the question is, how do we construct them? And to construct them, we use something that is called Latin squares and orthogonal arrays. So they are combinatorial structures that are, let's say, kind of easy to understand in their formulation. Besides that, actually, their construction from an algebraic point of view is very difficult. And we saw that already yesterday when we talked about the optimization of orthogonal arrays for with Boolean functions and evolutionary algorithms. So we start with this definition of Latin square. So a Latin square is basically a square matrix of numbers. And in this matrix of numbers, we have numbers that are going from 1 to n, where n is the side of our Latin square. And there is in particular this property that every row and every column are permutations of the set of numbers from 1 to n. So it's something that is a little bit weaker than a Sudoku, because in the Sudoku you also have the condition on the subsquare. Actually, if you look into that specific example, it is a Sudoku because it is also satisfying that condition on the subsquares. But in general, we are just happy enough with permutation on the rows and the squares. So if we fix a particular row, we are seeing all possible numbers from 1 to n exactly once in a particular order that might be random or not. So, well, these kind of objects exist for any n, and it is very easy to show their existence, because if you start from the first row 1, 2, 3, 4, and then you start to do cyclic rotation, then you continue like this, you will get, it is easy to see that you will get a Latin square in the end. So they exist for all possible orders. Well, before going into orthogonal Latin squares, let's see a very simple example of how to use secret sharing in a very specific setting. And the specific setting would be 2 out of 2 threshold secret sharing schemes. So what would be the idea? The idea would be that, let's say that we have our Latin square, the one that is constructed there is totally fine. So 1, 2, 3, 4, 2, 3, 4, 1, 3, 4, 1, 2, and finally 4, 1, 2, 3. So the idea is that the dealer is going to sample a secret between 1 and 4. So S would be, in this case, something 1, 2, 3, 4. Once he has decided the value of the secret, so I don't know, let's say 3, this would be S, okay? He's going to select randomly what? A row of the Latin square, okay? So let's say that he's going to take the third row. So this would be the row R. And then he's going to look inside this row, what is the column that contains the specified secret S. So in this case, it will be the first column, because 3 is occurring here, okay? So we have this column here, C. And now the dealer is going to give to the first player the row, and to the second player the column. So the first player, Alice, for example, will get 3, and the second player, Bob, will take 1. Now, in order to reconstruct the secret, they need to put together the share, because in this way they have like the coordinate of the rows and the column, and they can uniquely identify the secret that was here. We are assuming here that the Latin square is public, so also known to any external observer. On the other hand, if Alice, either Alice or Bob, tries to reconstruct the secret without knowing the other share, then he or she cannot do anything because, for example, Alice here knows the third row, but then we see that any possible value of the secret is equally likely because we chose this initial row that was randomly selected, and each of these rows and columns are permutation, so we are seeing all possible values. And the same is also going for the columns. So this is the reason why this is a 2 out of 2 secret sharing scheme. If we want to do something more complicated, well, in general, you can see that you can generalize easily these to n out of n secret sharing schemes. Instead of having a Latin square, you will have what is called a Latin hypercube. So you will have a n-dimensional hypercube, where if you're going to select to fix any subset of at most n-1 coordinates, then on the remaining coordinate, you will see again a permutation of all the numbers. So this is okay, but it is very strong because we are requiring all actors to participate and to share to combine their shares. So to do something more complicated, then we can use orthogonal Latin squares. And in orthogonal Latin squares, we say that we have 2 Latin squares of the same order, of the same side, and they will be orthogonal if by superposing them, one on top of the other, then you see all possible pairs in the Cartesian product. So here you see 2 examples of Latin squares of order 4, and if you are going to superpose them one on top of the other, then you will see all pairs 1, 1, 1, 2, etc. up to 4, 4 in a specific order. But the important thing is that we are seeing all of them, all of the 16 ordered pairs of the Cartesian product exactly once. Now, the existence question of orthogonal Latin square is a little bit more complicated because you say, okay, it is easy to see that for order 2 there are no orthogonal Latin squares because we only have 2 Latin squares, and these 2 Latin squares are not orthogonal among each other. But for the other orders, actually this was one of the toughest open problems in combinatorial mathematics since the times of Euler, back in 1782, where he was trying to solve this particular riddle. So he was saying, suppose that we have like a parade of 36 officers, and we want to arrange them. So these officers are coming from 6 different regiments, and they have 6 different ranks. We want to arrange them on a square 6 by 6, such that in each row and in each column there are no repeating ranks, no repeating regiments. So basically he was asking whether it was possible to find 2 orthogonal Latin squares of order 6. And surprisingly enough, Euler was not able to find a solution. But then, like at the beginning of the 20th century, by exhaustive search, actually, Tarry proved that it was impossible to solve this 36 officers problem. So there were no orthogonal Latin squares of order 6. Okay, this is just some other history, but basically the theorem that is quite curious about orthogonal Latin squares is that if you just exclude the orders 2 and 6, so 2 is easy to see, 6 is more involved to prove, but you can still show that there are no orthogonal Latin squares. So for all other orders, we always find a pair of orthogonal Latin squares. So this is a very curious mathematical fact. Now, what we consider is, let's say we are not going to consider the whole construction of how to do mutually orthogonal Latin squares, but what we want to gain in order to have 2 out of n secret sharing schemes is to have a set of n mutually orthogonal Latin squares. What does it mean, mutually orthogonal? It means that if you take any subset of 2 Latin squares in a particular family, then they are orthogonal. So they are pairwise orthogonal. So we have, let's say, a set of n moles would be something like L1, L2, etc., Ln. Okay. And such that Li and Lj are orthogonal for all distinct I and j. Okay. Now, what is the idea? So let me skip a bit of. Okay, let us go here. What is the idea? Suppose now that we have three mutually orthogonal Latin squares of order 4 in particular. So we have the first one. Well, no, I will just show them on the slides because we don't have that much time. So we have the first one, the second one, and the third one, and they are all orthogonal if you superpose them in 2 by 2. So in the setup phase, the dealer is going to choose again a row as the secret this time. Okay, so not a single number as we were doing in the beginning, in the initial part of this new lecture, where he was going to select a single number, a single entry inside the matrix. Here, the dealer is going to choose a row as the secret. So assume that we are going again to choose the third row as our secret. Now, he's going to randomly select a column. So for example, the second column. And this will single out 3 entries, 3 different entries, or not necessarily different, but coming from different Latin squares. So 1, 3, and 4 in this example, if it is yes. And these 3 entries will be the shares that we are going to give to our players. So in this case, we are considering a secret sharing scheme of the type 2 out of 3. Okay. So they are going to get those numbers. Again, all Latin squares are public. Now, in order to recover the secret, what they do, for example, the first player and the second player, they put together their shares, and then they see, okay, what is the set of coordinates that contains 1, so the first share on the first Latin square, and 3 on the second square. We know that since we are considering an orthogonal pair of Latin squares, then there is exactly one set of coordinates like that. So they can uniquely identify what is the set of coordinates, and thus the secret which was encoded by the row. And this holds also for other combinations of 2 shares. On the other hand, if some of the players by themselves try to determine the secret, for example, the first one, then it doesn't have any luck, because any single value appears exactly 4 times over the whole Latin square.
So now the secret is like column, row.
Yeah, the secret is the row in particular. The column is the random seed that we are inserting to determine the entries over the Latin square. So it is always the row. It could be also the column and the other way around. That's the same. But the important thing is that if you see any entry, then it will appear exactly n times inside a Latin square because of these balancedness properties. And the same goes also for the second Latin square and for the third Latin square. So any single player cannot determine anything about the secret because every possible value is equally likely. Okay, so this part using cellular automata we won't do, but let me see if I have, maybe I have a few slides more considering, right, orthogonal arrays. So to, let's say, conclude also this part, we can go back to, let's say, orthogonal arrays to say, okay, this is basically saying if you have a set of n mutually orthogonal Latin squares, then you can construct a threshold secret sharing scheme of threshold 2 and n players. But in general, for this case, Kn, what do? Here, instead of using Latin squares, we are going to use orthogonal arrays, OA. And orthogonal arrays we already seen like yesterday in a very specific case, that was the binary case. In general, an OA is defined by a set of 4 parameters, that is n, k, s, and t, and plus there is the index lambda, if you remember, and in this case it can be determined by doing n divided by s to the power of t. So what is the idea? The idea is that we have a matrix of size, again, n and k, so n rows and k columns, such that in each entry we have a symbol that is not necessarily a bit, like we said yesterday. So S is simply the cardinality of a particular set. So yesterday we said that X was in particular 0, 1. Here it can be anything. And actually we want this to be the largest possible because this will be the size of the secret space, let's say. So how many secrets we can share. Now, what do we want in particular? We want to have an orthogonal array of these parameters where the strength is t, which means again what? It means that if you're going to take any subset of t columns, then every possible tuple occurs lambda times. Okay, so it means that, for example, here we have t equal to 3, for instance, and we are going to select this particular subset of 3 columns. Then we want that each triplet of symbols over the set X occurs exactly lambda times, where lambda is defined by this formula here in order to get the numbers right, because this basically constrains what is the number of rows that you need to have. In particular, for secret sharing schemes, we want indexes equal to 1, because in this way we know that we are able to identify a single row starting from a subset of t columns, basically. And the idea now to use it for secret sharing is very simple. It's similar to what we did with Latin squares before. So the idea is that, for example, we are going to devote the last column of our orthogonal array to index our secret. So this will be devoted to the secret. And all the other remaining columns, so here, for example, we have P1, P2, P3, P4, will be devoted to the players. So here, for example, we have 4 players in this scheme. And we said that we have strength 3 in our orthogonal arrays. This will mean that we are going to get 3 out of 4 secret sharing scheme. Now, what does the dealer do? The dealer is going to select a secret, again, in a, well, not in a random way, but in whatever way he chooses, out from the set X. So let's say that X is not the binary set anymore, but it is, let's say, a set of numbers from 1 up to S. So in the end, you will go to select a number between 1 and S. And then once he has selected the number, then he goes to see inside this column what are the rows that contains that particular secret. So let's call it, maybe using S was not a smart idea because now we have S for both the secret and the number of symbols. Let's say that this would be, for example, M. Okay. So instead of using M here, M here, and M here, and here. Okay, so he's going to see for the particular secret S that he's going to select from X, where does he appear? Does it appear inside the last column? So it would be, I don't know, let's say that S will be, for example, here, 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 and here. Of course, here the fact that we are saying there are 4 rows, it's completely random, I don't know. It's something that is constrained by the parameters of the orthogonal arrays, but it's just for the sake of an example. So it will identify in this example 4 rows that contains the secret S in the last column. And after that, what he does is to distribute to the 4 players the corresponding entries in the rows. So here we will have, I don't know, B4, B3, B2, B1. These will be what is used by the dealer to determine the shares to be given to the players P1, P2, P3, and P4. So they will get these 4 numbers. Now, in a later stage, to recover this secret, what they do is that since we have strength 3 for our orthogonal arrays, then if they put together 3 shares, then they know, for example, if they're going to consider these 3 shares in this subset here, they know by the fact that the index lambda of the orthogonal array is 1, that there is exactly 1 triplets of values inside this subset of columns that contains those particular values of the shares. So they can uniquely identify this row here and thus also the secret. And again, it is that if they try to do it, for example, with 2 shares instead, you can show that the number of rows that have, let's say, 2 shares, 2 values that have been fixed is exactly the same as the number of possible values for the secret. So again, if this row here has been chosen in a random way with uniform probability distribution by the dealer, then the, let's say, the collusion of less than 3 players won't gain any information about the value of the secret. And this is the idea to, let's say, obtain in general K out of n secret sharing schemes. Okay, yeah, I think that we can stop here since it's past 15 almost. Do you have any questions? Everything looked clear so far? Okay, good.